Hello everyone, my name is Abhay Murgund and I'm a master's student here at Columbia University. Today I'm going to present my final project for the Nonlinear and Adaptive Control course. My topic is Nonlinear Adaptive Control for the chassis dynamic compliance for the next generation vehicles. So basically I've worked on a problem that is becoming more important for the future of modern electric vehicles. So I've designed a new control system that helps lightweight vehicles stay stable and safe on the road, even when the chassis frame itself is flexible and twisting. So let us move to the next slide to understand why this is such a critical engineering challenge. What is the main problem? It's like we are trying to solve. The biggest issue with electric vehicles today is what we call the weight penalty. So, the battery packs in the cars are extremely heavy. So, they can add up to around 400 to 600 kgs to vehicles' total mass. Because the batteries are so heavy, automotive designers are forced to drastically reduce the weight of the rest of the vehicle, especially the chassis, to compensate uh, the weight. But this creates a new problem called the stiffness conundrum. When we use lightweight materials like aluminum or carbon fiber, they are strong, but they are not as stiff as traditional steel. A traditional rigid chassis twists very little, usually that up to zero point 0.5 degrees, but a lightweight chassis is flexible, so it can twist to about 2 to 3 degrees actually during a sharp turn. So this creates a control gap. So traditional suspensions controllers assume the car body is solid and is also as a rigid block. They do not account for this twisting flexibility. So my project solves this by integrating finite element analysis data directly into a real-time adaptive control loop. To solve this, I first had to model the physics of the system. I chose to use Lagrangian mechanics. The reason I chose Lagrangian mechanics is that it is naturally suited for handling constrained systems like vehicle suspensions very well. The most important part of the model is the potential energy equation you can see on the screen. Usually, the potential energy is which just includes gravity and spring compression. But in my model, I have explicitly included the chassis strain energy as a variable torsional spring. If you look at the equation one, I set up the Lagrangian as kinetic energy. Uh, as the kinetic energy minus potential energy. And also in the equation 2, which defines the kinetic energy based on the mass and inertia. And equation 3 defines the potential energy, which now includes that special chassis term. This math sets the foundation for the entire controller design. Now, this slide basically shows the most unique part of my research. Previous studies in this field usually assumed indefinite stiffness to make the math easier. But here I am modeling strain energy with variable stiffness that actually change depending on our controller input. On the right side is the figure one. You can see the CAD model of the lightweight chassis I designed specifically for this study. In the figure 2, you can see the finite element analysis or the FEA simulation, which I did on Fusion 360. The colors show the torsional stress distribution when the chassis twists. I used this simulation data to derive a mathematical formula for the stiffness map. If you look at the equation 5, you can see that the effective stiffness is approximately 2000, 250,000 plus 15,000 times the input of U. This means our controller knows exactly how stiff the car is at any specific moment. After setting up the energy equations, I applied the Euler Lagrange equation to get the final dynamics of the system. This leads us the equation 6, which is the roll dynamics equation. This is a nonlinear equation that governs how basically the car behaves. So, uh, In this here, I is the inertia, C is the damping, which is fixed to around 2500. We also have the moment from external forces like lateral acceleration when you turn the steering wheel, and also M, which represents the disturbances like bumps or potholes. My controller needs to solve this equation in real time to keep the car stable. So now let us discuss the control design. To manage this non-linear system, I used a method called backstepping. I broke this down into two steps basically. The step one is the tracking error. Our objective here is very simple. It's like keeping the roll angle at zero. When the car turns, we do not want it to lean over or roll. So I defined error E1 simply as a roll angle, right? Step two is the velocity error surface. We need to define how far the actual velocity deviates from our virtual target velocity. This helps us calculate equation 9, which is the second error term Z2. This term Z2 essentially tells us how far our momentum is from where we want it to be. So using these error calculations, I solved the idle moment, which acts as a virtual controller input. In equation 11, you can see the formula for MIDL. This calculates exactly how much torque is required to counteract the rolling motion and cancel out the disturbances. But here is the trick. It's like we cannot just simply apply torque directly to a chassis. We have to change its stiffness. So in equation 13, I calculated the required stiffness needed to generate the moment. Then in equation 14, I convert that required stiffness into the actual control input U. This tells us the actuator exactly how many millimeters to move to stiffen the chassis correctly. Now I want to highlight two very specific logic blocks that I added to make the system very robust in nature. First is the active bracing logic. Sometimes the math might calculate that we need negative stiffness, which is physically impossible. If that happens, my controller overrides the calculations and applies maximum stiffness. It basically braces the car against the turn to prevent rollover. Second is the mass adaptation law. In a real car, the mass is never constant. You might have passengers or heavy luggage, so the mass can vary by up to plus or minus 30%. To handle this, I created an updated law shown in which is shown in the equation 16. This allows the controller to estimate the mass m in real time based on the tracking error Z2. So the car can effectively learn its own weight while driving. So of course, in the control theory, we cannot just say that it works. We have to prove it mathematically. To guarantee safety, I rigorously prove global asymptotic stability using Lupin's direct method. I defined a candidate energy function V, which you can see in equation 18. This function represents the total energy in the error system. Then I took the time derivative of this function V. As you can see in equation 21, the result is negative semi definite or less than or equal to zero. This serves as a mathematical proof that the system energy always dissipates over time. It guarantees that the tracking error will asymptotically converge to zero, meaning that the car will always stabilize. So now let us look at the actual results for the simulation. I tested the controller using ISO 3881 double lane change manual. This is an industry standard test that simulates quickly to avoid any obstacle. I compared my adaptive controller against a standard passive baseline suspension. You can, if you look at the table, the improvements are significant actually. For the peak roll, the passive car rolled at 1 degrees, but my controller kept it at 0.71 degrees. That is around 29% reduction. For RMS roll, which represents vibration and driver comfort, we improved it by around 67.4%. And the settling time was faster by 8.6%, meaning that the car stabilizes quicker after the actual turn. So now let us move on with the experimental plots. Let us visualize this data now. In the figure 3, you can see the transient response. The black dashed line is the passive baseline. You can see it oscillating quite a lot. The red line is my adaptive controller, and it is much tighter and reduces the peak roll by 29%. In figure 4, you can see the mass adaptation working. I intentionally gave the computer a wrong initial guess of around 800 kg, while the true mass was 1200 kg. The green line shows the estimated mass as the simulation runs. It climbs up and converges toward the true value, reaching about 87.5% accuracy by the end. So in the figure 5, the blue line shows the Lyapunov function decreasing over time. This validates the math I showed you earlier. The energy is constantly dissipating, which proves stability. And in the figure 6, I also want to show you which is the active stiffness modulation. The black dashed line shows the passive baseline, which stays constant at 200. But if you look at the blue line, you can see a rapid bang bang switching pattern. This is very important because it visually proves that the active bracing logic is engaging during critical moment. It instantly stiffens the chassis to the physical limit to stop the roll, like exactly how we designed it to be. Uh, now here we have two more important plots. Figure 7 shows the actuator control effort. You can see the signal hitting the limits at plus or minus 10 millimeters. This confirms that the active bracing logic is working. It is utilizing the full range of the actuator to keep the car safe during the most difficult part of the turn. In the figure 8, this basically shows the phase plane analysis. The black loops represent the passive system, and the red loops are my adaptive system. The red loops are much tighter and smaller. This visually demonstrates that my controller has better damping and converges to the equilibrium point with much faster than the actual passive system. So to conclude my presentation, this project has made four major contributions to the field. Firstly, I developed a real-time control loader that integrates FEA structural data into the loop. Second, we achieved excellent performance with around 29% reduction in peak roll and 67% improvement in RMS roll. Third, I also introduced the active bracing concept to prevent rollover during sudden reversals. And finally, I mathematically proved global asymptotic stability by Lyapunov analysis. So this framework allows next generation electric vehicles to be lightweight without actually sacrificing safety. So here are my references used for this research, including standard texts on nonlinear adaptive control and vehicle dynamics. Thank you very much for your time.